Well, thanks a lot. Today I'd like to actually tell you about non-flops, okay? The kind of arena in life sciences which really, the type of computing is really not measured in gigaflops or petaflops, but instead in other parameters that are important. And I'm going to illustrate this by a variety of different genome projects that are going on, and in particular focus on one area, which is the study of repetitive DNA, which is sequences in DNA in the DNA where the letters go CAG, 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 something repeated like that, which has a particular biological behavior. But because we are uniquely positioned to study this now, we're developing new diagnostic markers, drug targets, and toxicology tests. So before I get started on that, I want to tell you that I'm actually from Virginia Tech and an institute called the Virginia Bioinformatics Institute of about 250 people that are using computers to do biology, life sciences, and medical sciences research. And so we have 4 research divisions, but 2 primarily do HPC kind of calculations. One is the genomics group and medical informatics. The other is a group that does very large agent-based global scale models and simulations, largely of infectious disease in response to various crises. We also provide a variety of research services to the world, large-scale DNA sequencing, DNA analysis, or analysis of any biomedical data, and also HPC resources. For example, right now we happen to be sequencing, I just checked the queue, and we're doing about 20 or 30 pathogens, the camel, everything the camel seems to eat and be infected by, and the monarch butterflies happen to be going on this week. In addition, we have a business development arm which is largely to try and get the discoveries that we make out into the medical community, which means we have to start companies. And we have a significant education outreach, not just the fact that we have graduate students and such in, but we reach out to about 5,000 K through 12 students either going there or coming in to do a variety of different hands-on things, some of which include HPC efforts and some of which span entire summers. So we will have of the orders of hundreds of people in for the summer. Just to kind of let you know that some of the observations and things that are design constraints in doing HPC for the life and medical sciences is that it's a fundamentally different kind of game. First of all, you have to realize that most users of high-performance computing are really not developers and really don't have any sophistication or knowledge about how to do programming or anything else. But nonetheless, they use this HPC resources, and we try to keep it as black box for them as possible. This results, there's about 100,000 or so people who come and visit and use and kick off jobs that are on HPC class machines or doing analyzing data or using databases that we'd pre-computed results for, and this is about 100,000 or so a month. So the work is also very data intensive, and it's frequently done on large memory machines with lots of storage, and we have significant bandwidth requirements. Indeed, I'll tell you that the largest DNA sequencing group right now is in China. They've installed the largest capacity, and the largest bandwidth that we can obtain to get data from them to us is via FedEx. And so we ship arrays of drives to them, and they ship arrays of drives back. That's much larger than trying to shoot it over a wire. And I think that an effective high-performance computing facility in the life of medical sciences really has a mix of hardware types and architecture types, and organized development of an environment of tools that have some of the basic building blocks which are used in most biological calculations, and an organized and structured permanent set of data, things like all of the Medline, all of the GenBank, all the sequences that we can gather from the rest of the universe. And of course, we have to have developers that are computer and life and medical sciences savvy. And I'm going to show you a place where that kind of fails at times, and also a critical mass of investigators that have interesting and supported projects. So our current resources really are a mix of microprocessors, GPUs, and gate array systems. And these are all closely associated with data, in the petabyte range of kind of storage that we need just to kind of keep up. And this is supported by NIH, NSF, DITRA, DARPA, NVIDIA, and others, as well as a partnership computing group, which is really people can join us, help contribute to our hardware, and then get access to all this stuff up here, which is not only hardware, but all these other resources at one time. So to illustrate this, I want to just tell you about the 1,000 Genome Project, which is ongoing right now, and another genome project. The 1,000 Genome Project was launched in 2008, and it's really to sequence about 2,400 individuals over the 3 years, and so it's actually going on right now. And so the first genome, as you know, took 10 years to do and cost about $3 billion. For this project, the cost is around $10,000 per genome. And indeed, with the current technology using slightly less than perfect sequencing, we can get this down to about $800 today. So the technology is also evolving continuously. The DNA sequencers that are doing this didn't exist 3 years ago. They're changing every year, and they have phenomenal error rates when you look at individual reads. But when you actually look at a read of a sequence and you do it a few million times, you can get low error rates if you do that with that intensity. So not to be beat by the Genome Research Project of the NIH, the National Cancer Institute launched something called the Cancer Genome Atlas, which is going to sequence 200 forms of cancer, which means they're going to do a lot of patients, 200 different types of cancer, in both the tumors and the DNA from them that is not from their tumors. So they can, the value in this is that tumors, of course, are distorted, but were they born with something that is a predisposition to cancer? And so it will be very interesting, and we are studying and comparing these two sets of data. So what I'm going to tell you about is in our particular project, we have a goal to not only analyze all this data, but also to establish a robust, reliable set of microsatellite or repetitive DNA sequences. And I'm going to show you why I'm mentioning that this has to be robust. And then to begin to make observations regarding the underlying genetics and statistical distributions of these things so that we can find, as I said, drug targets and such. So what are microsatellites? I mentioned that these are motifs of sequences that fall within our 3 billion bases where they're repeated over and over again. CCTA, TT, CCTA, TT, for example. And microsatellites are, of course, have been used extensively over time. They, a very small number, although there's about 2 million or so of these microsatellites or repetitive motifs spread throughout the genome, about 20 of them are used in every forensics and paternity test that's conducted in the world thousands and thousands of times a day. However, there's much more activity in these other than these 20. They're extremely variable. They tend to be 4 orders of magnitude more variable than single base variations within the genome. And they also tend to be very understudied for a number of reasons, mainly technological, that has to do with the reliability of making these DNA calls. So the analysis of all the human genomes to date have really focused on changes in single bases called SNPs. And so, however, if the results from the Human Genome Project has been somewhat disappointing in the fact that it was anticipated that the Genome Project would reveal all these variations and we would understand all the heritable components of disease. However, there's a very large discrepancy of about 50% between the known heritability of a disease, knowing that it has a genetic component and what amount it should be, and that can be explained by SNPs, which has been the focus of virtually all the groups. So, however, if you actually start looking beyond these single base variations and look at microsatellites, they might be this missing heritable component, because microsatellites have indeed been implicated in disease. For example, they're the causative agent that cause, for example, Huntington's disease and a number of other things, Fragile X. But because they're hard, they're difficult to measure, especially in mass, people have not actually looked at these things. So we did, and This is an illustration of looking, for example, the horizontal axis here. Each of these happens to be one particular human genome sample that is either a tumor or a germline or DNA that comes from the blood of a person who happens to have cancer. These happen to be informative DNA motifs that are integrated on a global scale, looking at every place they exist in a genome. And I think that you can probably see very easily that this half looks very different from this half, okay? This half is primarily composed of breast cancer patients, both tumors and the blood that they were born with, okay, as well as childhood liver and a number of other, and some cancer-free volunteers. It's very difficult to find real controls in cancer, as you know, because it may just be that you haven't gotten it yet. Okay, if you live long enough, you probably will. This particular side is dominated by people without cancer, and also particular types of cancers. For example, BRCA1 and 2 happen to be one gene defect that is very much coupled to breast cancer and explains about 40% of the heritability. So it turns out that this must be a fundamentally different type of cancer that is induced from those that actually cause instability on a global scale at these microsatellites. In other words, they're changing in tens of thousands of places in the genome. And so suddenly, what we have is this particular assay alone allows us to, first of all, we can distinguish most cancer, people with a risk of cancer from those that don't have a risk, because again, these are patients' germlines. And we can also certainly account for about 10% of the variation in breast cancer alone, just with this. So this is the power of doing genomics on this particular scale. So with the 1,000 Genome Project launch, that was internal data, but with the 1,000 Genome Project launch, we can take advantage of the fact that a lot of sequencing is done for the world community and can be analyzed by anybody who wants to go out there and get it. You only have to get about 6 to 10 terabytes a day in order to kind of keep up with it. So the 1,000 Genome Project is really was really designed fairly uniquely. And one of the first tests they did is they actually sequenced 2 sets of families, mother, father, daughter, mother, father, daughter. And this allowed people to actually test some things. For example, the daughter should inherit 1 copy from the mother and 1 copy from the father, provided that you know the father correctly. And about 15 to 20% of the time in virtually all genetic studies, you don't. But nonetheless, this was confirmed. But when you had that, we were actually able to study and look at the microsatellite content from the assemblies that are provided using the raw data from these 6 individuals. We found out that 80% of the loci that were informative did not exhibit this inheritance, this Mendelian inheritance of the mother and father going into the daughter. We found out that really this was a consequence of the fact that all current assembly engines for the Genome Project, every single one of them makes assumptions and does all the microsatellites between unreliable and wrong. And so this is 2 million places in the genome where this is an issue. And the reason why I bring this up is that largely it was bad assumptions and choices by the programmers who happen to not know genetics who developed all these codes. And for example, it just so happens that one primary error that's made here is that when there was insufficient data to make a call at a particular place in the genome, instead of actually saying, we won't make a call, it just goes back to the reference genome, which happens to be none of the genomes that were actually sequenced, and goes and gathers that particular sequence and happens to insert it in place. So this is one of those cases where it'd be best to have nothing than to have something that's wrong. So we developed a more stringent approach to do this, which takes into account the particular density of data, and it allows us to actually boost this to about 95% of these things actually do obey traditional inheritance. And that's about right, because there's about a 5% or so spontaneous variation within the genome from one person to another. And so this now allows you to actually make observations for where you could make real discoveries. If you have 80% of your data being wrong, or error, it's worse than error, it's wrong, then it's very hard to make any correlation whatsoever. This is the reason why, and so in the 3 billion letters, we actually are focusing on doing small reassemblies at 2 million places that happen to span only a few hundred bases long. And so there happens to be a repetitive element. If there happens to be a repetitive element, the way in which assembly is done is that modern day next generation sequencers read only about 75 to a couple hundred bases in each individual read. And those things have to be assembled by overlapping sequence to get the 3 billion letters of continuity. If you're reading a single letter like a SNP, and it happens to be right here, that single letter would be reinforced by 2 particular reads, which would be good. However, this particular microsatellite is really only covered, it may look like it's covered in places by 3 reads, but these reads here and here are really irrelevant at those loci because they actually don't span both sides. So you don't actually cover the part that's repetitive. And as you know, if you have something that's CAG, 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 you can always insert another CAG and not really know what the true length of it is. So we go on to actually, to develop algorithms that throw out all the rest of these things and then reassemble the genome in 2 million places. This has resulted in developing a flowchart that uses some of traditional codes like BLAST, and also there's a code called a BWA. And so this, for every genome that is being sequenced, we are taking all the raw data, which typically has 100 to several hundred million individual reads of 75 to a few hundred bases long, and redoing every assembly. And just to give you, and so this means that we're doing 2 million reassemblies for thousands of genomes, and when that's done, we actually can do data mining. Now, to give you kind of an illustration of why it's really necessary to have a variety of different architectures, hardware architectures and software architectures, there's a particular part of this code, BWA, which is compute intensive, it's the align part, on a 4 gigabyte file, which is about 14 million reads. It takes 2 minutes on a Convey HC1, which is an FPGA, or 4 hours on a single node of a standard machine. Now, this may sound a little unfair in the fact that it's only a single node on something that has a lot of cores here, but this code won't run on all the cores effectively, and it's been and people have worked to try and do that. Indeed, we're actually working to improve parts of this code on FPGAs, on graphics processors, and on standard processors, and we are going to end up building hybrid computational codes that do particular things, but will have certain parts that go to one architecture and to another and bounce back and forth depending on which one happens to optimize which part of the code the best. Once this is done, for example, here's some summaries of some genomes. This happens to be the Utah father and mother and daughter, and here's the Nigerian. And one thing that you can see is that for all these microsatellites, about 1% of them are variable in any genome. So there's 2 million of those in a genome. The difference between one person and another, you can do the math, there's 1% or so. Having this kind of information is really good to understand genetics on a global scale, but what's really important is being able to make decisions on an individual or personalized medicine scale. If we were to actually look at particular variations that we observed in this data, once it was made highly reliable, here's the daughters of these particular families, and it turns out that for this particular Utah daughter, we actually know that she has an elevated risk for breast cancer because she has a particular variant in a gene for which has already been known to as a diagnostic for that. Now, this particular young Nigerian daughter has a particular variation that gives her a very elevated possibility of being schizophrenic. Plus, she has a particular variation in a gene that gives her protection against inflammatory and immune diseases, But only if this gene, if she has this variation, but only if she also happens to be infected with hepatitis A does she get this protection, which is an odd thing about genetics. Now, the interesting thing is about something like 80% of the people in Nigeria have hepatitis A. So this is a very informative thing about this particular daughter right here. So we can actually make clinical decisions about these people right now if we knew who they were. Okay, that's an important thing. All this data is anonymized. Now, another phase of the 1,000 Genome Project is where they focus not on the entire genome, but looking only at those regions that actually code for proteins at the 20 to 30,000 genes or so. And this has been done on a much larger scale with 700 people in a variety of different populations so we can understand the variation between different population groups. It turns out that using these various technologies, only about 570 out of the 700 genomes are actually possible to look at the microsatellite or hypervariable regions at all because of the limited read lengths. Once we did that, we've actually rebuilt these, all of these. So we looked at a total of about 3,000 microsatellite loci in these very important gene regions, and we found about 9,000 variations in this entire population of 570 people. But all of these 9,400 variations were restricted to 31 different places in the genome. Okay? And so this averages about 16 variations per genome out of this 3,000 different places that we looked. Now, none of these particular variations were identified using the standard variant calling methods. And we also went back, because you can go and ask for DNA from these particular things, from this particular group, and went back using traditional DNA sequencing to verify it. Now, the last thing is that 60% of these particular variations had been previously documented and were known, but that means that 40% are entirely novel, and so every time you do an experiment like this, you can make novel observations that could really impact our medicine and genetics. Now, of all those different variations, there was a substantial number of them directly in proteins that actually change one particular protein amino acid to another or delete it. And you can see that that some of them have, for example, 53 of the people happen to have this variation, but most of them are individual singleton variations. And so we could make, for those 570 individuals, various medical predictions and medical suggestions for them today if we knew who they were. But where are we going from now, from all that? So I've already told you that having established a robust routine to do this, we just simply have to have the computing power and the bandwidth and funding to just get all this kind of data in and to do something with it, and then to put it back and try to feed it back into the government so they can overlay these new assemblies onto the existing public database, and so that everybody can play and get information out of this, and people who are much wiser than us, who are the cancer and the various disease experts in the world, could use this data. So we're in the process of doing that now. But an important thing is, I've already told you that there's this Cancer Genome Atlas data, which is they're sequencing, as I said, 200 different cancers in a lot of different people. The 1,000 Genome Project, is really composed of randomly selected individuals who are supposedly free of disease, but nobody is. But nonetheless, if you do enough people, you can get an understanding of what the basal level of variation is within the general population. And then, if you actually compare that with all the cancers where you've actually enriched for people who have cancer entirely, you're able to inspect each of these 2 million different places to see what are the differences in the distribution functions, and that's what is going on right now. And just to let you know, it'll take a little while to do this, but I'll send you a copy of the paper if you want to know in a few months or so. So there's a few calculations we have yet to do. The other thing is that it turns out that just simply analyzing the data is not enough, that we've actually devised some new techniques to actually enrich for particular areas that we're interested in sequencing, and then going ahead and sequencing them on our own instruments to actually overlay new data on top of this public data to make certain that we're making all these calls. And since we're since we're doing this not only for cancer, we're doing it for a variety of other diseases, I just want to tell you that it turns out that that neurological diseases happen to be another class of diseases often associated with these particular varying parts of the genome. And I just want to tell you that although no one has found a gene for autism yet, I just want to let you know, stay tuned. We'll be publishing that shortly. All of this particular stuff ends up being great discoveries that you can throw back into the public database. However, because it takes roughly 15 years and $1 billion to take any discovery, any target, any finding, to make it a new therapy or drug, you have to actually commercialize this and be willing to work with the drug companies that happen to have $1 billion to do these kinds of things, to take any single discovery forward. We launched a company 2 weeks ago to house all of this, all of the findings of these mining these public databases using codes that actually do it correctly, and to start devising new drug targets for pharmaceutical companies to target. All right, thank you very much. So.